Alright, so hello again everyone. So welcome again to another science lesson discussion. And today we will have a brand new topic and our topic is under physics. Alright, so hey, so before we have this one, so if you are familiar with Isaac Newton, so this topic has something to do with him. Okay, so let's get this over with. Okay, so Alright, so what we have right here is the famous three laws of motion formulated by Isaac Newton himself. Okay, so in this particular lesson or topic that we will going to discuss, we will have the basic ideas of and basic concepts of Newton's three laws of motion and its practical application in real life. Okay, so let's start. Okay. All right, so this is Sir Isaac Newton, and he lived from 1642 to 1727. All right, so this he is a well-known person in terms of in science. All right, in physics especially. He developed calculus. All right, he developed calculus. He discovered the spectrum of light. All right, that white light is somehow made up of several frequencies of light. All right, and also the three laws of motion that we were going to discuss today, the law of gravitation, and so on and so forth. All right, so he did all of this. He did all of this during his free time. All right, so and upon that, he published a book named Mathematic Principles of Natural Philosophy. All right, so in there are the things that he discovered in math and science written in a book. Okay, so what he said here is, if I have ever made any valuable discoveries, it has been owing more to patient attention than to any other talent. All right, so what he is showcasing here is his patience. All right, his patience in solving or attention to detail, in getting the attention to detail in his observation. All right, that what made Isaac Newton very successful in this particular career. Yeah. All right. So that is Isaac Newton. And with that, let's start on let's start our discussion with his first law. All right. So the Newton's first law, also known as the law of inertia, law of inertia. All right. So what is inertia? Inertia is a property or property of matter. All right, property of matter, or to be particular, any matter that has a property called mass. Yeah, all right. So any matter that has mass, and all of them has what they call inertia. What is inertia? This is the tendency, all right. This is the tendency to resist any changes in terms of velocity. All right. So this is the tendency of an object to resist any changes in velocity. All right. So what does the first law what does the first law states? It states that an object at rest, it tends to stay at rest, and if an object is in motion, it stays in motion unless acted by an unbalanced force. Now, what we will try to find out here in this particular first law is the unbalanced force. What makes this very important in order for an object to not to stay at rest and to change direction when it is in motion. What is this unbalanced force? All right. So okay, if we take a look at this, when a car hits this wall, all right. So what do you think will happen? All right. So if the car is moving faster, right, going that way, and if it hits the wall, automatically the car will stop, right? So the car will stop, and the person inside that particular car will fly away. All right, we will fly away from the car. All right, it will go right there. Okay, when it hits that wall. So that this particular scenario. All right, this particular scenario tells us what the first law of motion is all about, or the law of inertia is all about. All right, if an object is moving and there is an obstacle here, which is the wall, and it hits the wall, and if the object is moving along a straight line and if it hits the wall, it will make an unbalanced force. It will create an unbalanced force, and therefore the car will stop. Right? Same thing with the person inside. The person inside the car is at rest. Then after the car hits the wall, so it will create an unbalanced force. Then therefore the person inside will fly away from the car. So it will go from rest to, or it will go from acceleration from, or it will move. Okay, the person will move from rest. All right, so that is how this one works. Next one. All right, so basically an object will keep doing what it is supposed to do, all right, unless acted by an unbalanced force. All right, so if the object is sitting still, all right, if the object is stationary, it will remain stationary. If the object is moving, it will remain in motion, unless there is an outside force that will interact with the object, that will make it move if it is stationary, or it will change direction if the object is moving. All right, so all you need to do is it takes a force to change the motion of that particular object. So to give you one example, if you want to change the direction of the train, if you want to derail a train, you need a lot of force to do that. All right, in order to remove the train from its track. Okay, so that is what the first law was all about. All right, so if you take a look at this book, all right, if you take a look at this book over here, sitting on the table, all right, the book is experiencing equal and opposite force. One force here is the upward force that you see here, the up arrow here is the normal force, and the second one, the down arrow, is the gravity. Right, so the gravity. So these two are very important because it makes the book stay on its place. All right, so the book is experiencing equal and opposite force coming from two direction. But if you remove the table, what will happen is the force of gravity will be greater than the normal force. So the book will fall down to the floor. All right, so that is not anymore balanced. That is now unbalanced force. All right, this is what the law of inertia is talking about. If there's an unbalanced force, it will create, all right, it will create a situation where the object will likely to move or change direction. All right, so okay, another example is a soccer ball. A soccer ball will not move unless you kick it. All right. Next one is the tug of war. All right. If the force is equal on both direction, all right, on both opposite direction, so therefore there will be no motion that will happen between the two teams that you have right here. But if you add something here, and if you had a team here, so the force will now be greater on this side, so therefore the team here will be the force here will be unbalanced, therefore this team will move that way. All right, so that's how you change the situation or the scenario of a particular object, so from stationary to motion. Okay, so alright, so this picture is an effect of an object that gains a lot of momentum. Alright, so that gains a lot of momentum, and it this object is placed on space. This is a steel block. This is a steel block which is hit by a baseball-sized space debris. Alright, which is hit by baseball-sized space debris. So if you imagine that object is moving several velocities several velocity faster. Yeah. So as it hits this steel wall, so what happens? It creates a crater like the one that you see here, and well, okay, the object contains a lot of energy. All right, so that's how that object creates this particular crater on this steel block. Right, only if the object is moving in a straight line and even though it is in a small mass. All right, if the object is moving faster, what will happen here is the object will have a greater momentum. Alright, even though its inertia is very low because of its mass, alright, because of its mass, but in terms of momentum, it will create greater destruction on a piece of steel that you have right here. Alright, next one. Okay, so if you are familiar with this particular trick, so the coin trick that you have right here, alright, so you expect what will happen if you expected already what will happen to the coin if you remove the paper below it. Alright, so alright, if you remove the paper below it by tapping it out. Alright, so by tapping it out, so what will happen to the coin? It will fall down. So this is what the first law is all about. Alright, the object is at rest, and once the paper is in there, as long as the paper is in there, it will be at rest. But once you remove that particular paper, it will create an unbalanced force. Then the coin will fall down following the gravity, the direction of the force of gravity, which is downward. So basically, the coin will fall down. All right, in this particular experiment. So another one is the golf ball. As long that there's no golf club that will hit this golf ball, so the golf will not move. All right. Now, once it is hit by a golf club, when it is hit by a golf club, it will travel, but not in a straight line. It will go back again to Earth. All right. It will go back again to Earth, and that is because the ball encounters gravity and air resistance. Now, when you do this one in space, when you do golfing in space, the golf ball will not go back again to Earth. It will travel along a straight line. It will travel on a straight line unless some external force will interact on it that will change its direction. All right. So that is the first law of motion. Okay, in this particular video, although it is a hilarious one. All right. So this is the particular trick where you can remove the tablecloth without affecting the utensils and other dining materials on top of the table. All right, except this guy over here. All right, so that is the first law of motion. So if we take a look at this one, okay. If we take a look at this scenario over here, okay. Right, so there you go. Okay, so if we try to do a simulation about the first law of motion, so let's try this one. So this is sponsored by PHET simulation. All right. So later I will just include the link on the description. All right. So the object is in stationary. All right. The object in stationary. If you apply an external force on it going this way, the object will start moving. All right. So the object will continue to move, as you can see on this simulation. It continues to move, all right, unless you act a different force or an opposite force that will change its direction. All right, so as you can see, the object is moving to this direction earlier, right? The object is moving to this direction earlier, and when we applied force that is going to this direction, right, to the left, right, what happens is the object starts moving to the left. Alright, so that is what law of inertia is all about. Alright, so okay, there we go. So next. Okay, so okay, another school experiment tricks or school standard school experiment. So we have here a 4 ball. Although it is a very, it is unfortunate that the other ball did not went inside the glass. All right, so that is another experiment related to the first law of motion. All right. Next one. Okay, in practical application, in daily application, the first law of motion, it is used in the application of seatbelt. All right. So in this particular scenario, the woman at the back doesn't have any seatbelt. All right, did not wear her seatbelt. And what happened when the driver suddenly stops or suddenly crashed onto something? So what happens here is the woman starts moving. All right, in front. Okay, so please wear your seatbelt, guys. Yeah. Okay. So next one. All right, so let's answer this question. Why was it that we cannot stop the Titanic from colliding the iceberg? All right, why is it difficult to stop the Titanic with colliding an iceberg? All right, it's because Titanic is massive. All right, as we all know, mass is related to inertia. All right, so which means that the greater the mass, alright, Titanic is very large, so inertia is directly proportional to mass. So meaning to say, the greater the mass, the greater the inertia. Alright, if an object has a smaller mass, alright, so expect that the object has small inertia. Alright, so mass and inertia are related to each other. Don't forget that one. Alright, next one. We have here the second law of motion, or also known as the law of acceleration. Alright, so in this law of acceleration, it tells us that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to mass. So if we put this statement into an equation, it will look like this. Alright, so it tells us that acceleration is directly proportional to force, and acceleration is inversely proportional to mass. Alright, so if we combine this two relationship together, we can come up with this particular formula. So rearranging this formula will give us force is equal to mass times acceleration, whereas force is equal to Newton. Remember that force is anything, it is a push or pull. All right, so newtons, which is in capital N, right? Sorry for this one, newtons. Then we have m for mass. All right, so it is in standard kilogram. And we have the acceleration. We have acceleration over here, and it is in meters per second squared. So don't be confused. Don't be confused by velocity. Velocity is meter per second, and acceleration is meter per second squared. All right, you can rearrange this one. You can rearrange this one to get the mass. So force over acceleration. So with this three formula, you can now encounter, or you can now solve any problem that is related to acceleration, force, and mass. So how do they become related to each other? So the greater the mass, the greater the force you will apply on that mass in order to move that mass from 0 to 1 meter per second. All right. So in order to accelerate it to 1 meter per second squared. All right. So the lesser the mass, the lesser the force you require. Right. Next one. Mass. The greater the mass, what will be its expected acceleration? Since it is inversely proportional, it is less. And the smaller the mass, the greater the acceleration that particular mass can achieve. All right, so this is the second law of motion, the formula 1, 2, and 3. All right, so okay, before I forget, there's a difference between mass and weight. Right? So do not be confused with mass and weight. When we talk about mass, this is the amount of matter in a substance. Alright, so that's the amount of matter in a substance. For example, molecules, atoms, and so on and so forth. Alright, when regards to the weight, weight is a force. Alright, weight is a force that is acting on an object. Alright, so force of gravity that is acting on an object. Alright, to be exact. Force of gravity that is acting on an object. So what is that? So if you take a look at this formula, alright, we can use this one for weight. We can replace the acceleration. We can replace the acceleration to become g. What is g? This is the acceleration due to gravity on Earth. In different planets, they have different acceleration due to gravity. We have here 9.81 meters per second squared. Alright, so when someone asks you what is your weight, if you answered 55 kilogram, that is wrong. Alright, that is your mass. Alright, that is your mass. What is your weight? 55 kilogram times 9.81. Alright, so let me get my calculator. Alright, 55 times 9.81. So that is 540, more or less. 540, that is newtons. This is your weight if you are 55 kilograms. If you are higher, so you can get a weight of higher than this one that I have right here. All right, so weight and mass are different. So do not be confused on that. All right. So basically, an object that has greater mass, all right, and it changes its speed very slowly. So meaning to say it has low acceleration. Will have a greater force. All right. Example: the glaciers or the avalanche. All right. So since ice packs are greater in mass, so it still has it packs a lot of force. Right. Next one. An object which is very small, just like this bullet over here. Yeah, just like this bullet over here. So it has alright, it has a very low inertia. Alright, it has a very low inertia because it has low mass. But, alright, it has greater force. Because the bullet is moving quickly in one direction. Alright? So, the bullet is moving quickly in one direction. So, it has a great force. But an object with small mass, if it is moving very slowly or if it is accelerating very slowly, if it is accelerating very slowly, the force of that object is also less. Alright, so please take note of that. Okay? The only thing that will make a small object to achieve a greater force is to move it, to accelerate it very, very fast. Alright. So just like what you have here on the GIF image. Alright, so as you can see, the man here doesn't have enough force to push a massive truck on the left. Alright, next one. Okay, meanwhile, although it is hilarious, okay, so these three people over here exerts greater force in a smaller mass object. Right, in a smaller mass object. So therefore, they'll be able to push that car forward. Okay, so let me repeat again. Greater force is required for an object with greater mass, and smaller force is required for an object with smaller mass. All right, next one. All right, so which one do you think? If these two vehicles will race, all right, will race head to head. Which of these two objects or two vehicles will go faster or starts first, right? Will move first. Okay, so which of these two objects or two vehicles will move first? Is it the race car or the airplane? Alright, so by following the law of acceleration, an airplane, this fighter plane that you have right here has greater mass, so therefore it will start slow. Alright, meanwhile, this one will start fast because the race car has smaller mass, so it requires less force in order to start first. But if the race ends, who do you think will win? Airplane or the race car? Okay, so definitely the airplane. It's because once the airplane accelerates, it will create a once the airplane achieve the force that it needs in order to accelerate faster, there will be the race car will have no chance of defeating it. All right, it's because even though the car will push through its limit, the force needed here is not enough to counter the force that is needed to push a massive object like the one that you have right here. Right? So that at the end of the day, the airplane won. The airplane will win a race between the race car. All right? So with the race car. Okay. So that is the law of acceleration. So law of acceleration, force is equal to mass times acceleration. All right. So let's try using the force is equal to mass times acceleration formula in this particular sample problems that we have right here. Suppose on the first problem, what acceleration will result when a 12 Newton net force is applied to 3 kilogram object and a 6 kilogram object? So what we will use here, so we have here mass of 3 kilogram and force of 12 newtons. Alright, so what is missing here is acceleration. Alright, so we have two mass, by the way. So we have 6 kilograms and the force. Alright, so 6 and 3 kilograms. So what are we going to use here? So we will going to use the formula F over M. So using this formula, we will get 1.4 meters per second for the 3 kilogram object and 2 meters per second squared for the 6 kilogram object. So if you happen to notice, the object with lesser mass, right? So the object with lesser mass, right, requires or starts with an acceleration, all right? Acceleration which is somehow less than, all right, than the other one, all right, than the object with greater mass like the 6 kilogram, right, that we have right here. So remember that greater mass will require smaller mass requires greater acceleration, all right, and we have right here this greater mass, all right, requires less acceleration. All right. So let me repeat that one more time. Okay, smaller mass, since they are inversely proportional, smaller mass will need to have or will gain greater acceleration. All right. Next one, greater mass will yield smaller acceleration. All right. If we follow the inverse proportionality between the mass and acceleration. Let's go to the second problem. A net force of 16 Newton causes an object to accelerate at a rate of 5 meters per second squared. Determine the mass of the object. So what is missing here is the mass. And what do we have right here? So we have 16 Newton and its acceleration of 5 meters per second squared. Alright, so if we use the formula mass is equal to force over acceleration, so we will get, so we use our calculator here, 16 divided by 5, we have 3.2 kilograms. All right, so 3.2 kilograms. Okay, so next one. Okay, so how much force is needed to accelerate a 66 kilogram skier to 1 meter per second? So sorry for that. Right, so 1 meter per second squared. So obviously, so we have force, which is missing. We have mass, which is 66 kilogram. And we have acceleration. We have acceleration of 1 meter per second squared. So if we use the formula F is equal to ma, alright, so we will get 66 newtons. Alright, so in order to move that skier of 66 kilogram to 1 meter per second squared acceleration, you need 66 newton force in order for you to do so. Alright, so that is Alright, so that these are the problems that you might likely to encounter, and will be able to you will be able to utilize this particular formula coming from that second law equation. Alright, so we go now to the third and last Newton's third law. Alright, the Newton's third law, are also known as the law of interaction. Alright, so that's the law of interaction. Alright, so it is stated simply as for every action, there is an equal and opposite reaction. Alright, so for every action, there is an equal and opposite reaction. For it means that if a force is going this way, there is another force opposite to that force that is going on the opposite direction. All right, so that is the Newton's third law. Is what this law of interaction is all about. All right, let me give you one example of that. So sitting on a chair is an example, is a very good example of Newton's third law of motion at work. Yeah. Okay, so let's put object A as the person, and the chair will be object B. If object A exerts force downward, alright, on the chair will exert force upward to the person. Alright, so this is a mutual force. Okay, this is a mutual force, opposite direction. Alright, so another example is when you push the wall. Alright, although the wall is not moving, but the wall is exerting pressure, not pressure, it is exerting force towards you. Alright, it is exerting force towards you. So, as you push the wall, alright, the wall is exerting force at the opposite direction. Alright, another example is walking. Alright, walking. If you walk forward, alright, the ground is also doing an opposite force for you. Alright, so that is friction. That is what they call friction. Okay, so although this meme is hilarious, but it clearly follows the third law of motion. And by the way, there are two forces under this third law. We called it the action force and the reaction forces. Okay, so later I will show you how this is done. Okay, next one. Okay, an example of third law. All right, Newton's third law in motion is the flight of the birds. All right, so the wings will flap. All right, it will create a force. All right, it will create a force downward. So the air underneath that wing will create a force upward. So this is the air and this is the wing. All right, flapping. So the force is mutual and it goes to opposite direction. That is why the bird achieves flight. All right, it gives a lift. That's the reason why the bird can change its somehow elevation. All right, or altitude rather. All right, so that is the third law of motion. So next, gun recoil. All right, so as you can see here, all right, the woman, all right, did not anticipate the recoil of the gun. Okay? So what is the action force here? The action force is the bullet is going that way. Alright? So the bullet is going that way. What is the reaction force? The gun is going that way. Right? So that is the reaction force. The bullet is moving that way. Right? It will exit the muzzle. Right? It will exit the muzzle of the gun, and the gun will, because of that force, okay, it will move the gun through this direction. So achieving the third law of motion. All right, next one. All right, rocket engines are also following this third law of motion. All right, so okay, so hot gases is pushed downward, right? So this is your action force. This is your action. Okay, what will be the reaction of that? As the gas pushes downward out of the rocket, right? The rocket is propelled upward. This is your reaction. Okay, this is now your reaction force. Alright, so without this particular set of forces, you will not be able to lift a rocket from Earth to space. Alright, so another one example is the jet engine. Yan. So this is the jet engine. Alright, used in most airplane. Okay, and how does it work? It works similarly as the rocket itself. All right, so the gases that is produced in the combustion of jet fuel creates an action force going this way. All right, so it creates an action force. So this is the action force. And all right, upon doing so, right, upon propelling those gases that way, the engine is most likely to be pushed forward. This is now your reaction force. All right, so the engine is pushed forward. So that is why you be able to travel on the airplane be able to travel on air because of these two forces that you have right here. All right, so let's use again our simulation. Right, so let's use again our simulation to better visualize what we are talking about. Okay, so okay, if the object has less mass, all right, so for example, this box has a 50 kilogram mass. All right, if you apply force on it, if you apply greater force on an object which has smaller mass, right? So what is the speed of that? All right, so let's put a value. So that is 21 meter per second. All right, so let's reset this one again. Take note of the speed. Now let's replace the box with a more massive refrigerator. All right, something like that. So the refrigerator has a mass of 200 kilograms, and what will be its speed? Now, if we follow the law of acceleration by Newton, its speed should be somehow less. Okay, because it has a greater mass. All right. So let's see if we apply the same amount of force as we did on the. All right. So as we did on the box earlier. All right. So what is the speed? All right. So the speed is 3.3 meter per second. Okay. So upon applying the same force, we have 500 newtons. We applied also. So let's try out. All right. So let's try out a more a lighter. All right, a more lighter object, and we will push this one. We will push this one the same force as those two objects earlier, going on the same direction. All right, so what is its speed? All right, so the speed is 14.7 all right meters per second. Okay, so is this speed is quite higher or much higher than the refrigerator that we had earlier. All right, so let's take a look at the acceleration simulation. Okay, so if we take a look at this and somehow put the masses there, so if you push a 50 kilogram box going this direction, all right, and if you notice its acceleration, all right, so in a frictionless force, in a frictionless floor, all right, so you notice that there is a friction going to the opposite direction. We will talk about that one earlier. So what is the acceleration of the object? All right, so I forgot to click this one. So let's start it again. Okay, if we push the object at same force, 500 newtons, so the acceleration is, all right, so the acceleration is negative. Right, so let's remove the friction. All right, for you to see the effect. Okay, let's push it again one more time. All right, so the speed is, all right, the speed is 11 meters per second and it doesn't accelerate. All right, so if we push it again, okay, so let's restart and let's put it none. Okay, so if we push this one, all right, you as you can see, the acceleration is greater. So if you put amount of force, right? Next one. How about we try? Right. So how about we try this one? Right. So how about we try this one and we push it? We push it using the same amount of force that we have earlier. Right. So let's stop this one from moving, and let's change it to refrigerator. All right. So this is this is a massive object compared to the first one. So if you put it on a frictionless floor, so if you push it, all right, the same force. So as you notice, the acceleration is less than the previous one, 2.5. The other one is 10, right? And as you can see, a massive object, all right, a massive object has less acceleration and you require greater force in order for you to achieve that certain acceleration that you had earlier. All right, so finally, let's take a look at the third law of motion. Okay, so if we put a friction or if we put okay, if we put an object on a friction, a floor with a or rough floor that we have right here, it will create a lot of friction. So let's see if the third law of motion states that if the statement of the third law of motion is applicable on this particular situation. All right, so let's have the speed, the mass, and its value. All right, so if we push, all right, if we push this box going this way to the right, so it will likely, all right, okay, so if you happen to see this one, the friction is opposite to the direction of force that you applied. All right, and that is 94 newtons. All right, so that is the amount of friction. Okay, now if we somehow, if we change this one, all right, so what happens to the object before I remove? What happens to this object? All right, does it continue to move? So as you can see, it doesn't move anymore. All right, it didn't move any further because there is an unbalanced force acting on the object, which is the friction. All right, the friction is the force that we are talking about here. That's the reason why if the object that is in motion suddenly stops. Okay, if we put the refrigerator on that same friction, a floor with a rough surface, and apply the same amount of force that we did earlier, and it doesn't move. All right. It doesn't move. Why? It's because, alright, it doesn't move because the force itself, alright, is equal to the amount of friction force that the floor exerted on the object. So, if we go back again to the first law of motion, it states that if there is if there is an unbalanced force only, that's the time that the object will move. Now, in this case, we have a balanced force. We have a balanced force, so that is why the object didn't move on any direction. All right. So basically, that is the Newton's law of motion. You can download this simulation on the PHET website. All right, so I will put it on the description in this video. All right, so with that, let's go back again to our PowerPoint. All right, so with that, okay. Alright, so let's summarize everything that we have learned today. Alright, so the Newton's first law of motion, it states that the object is in motion and it stays in motion. And if the object is at rest, it stays at rest unless they are acted by an unbalanced force. Alright, so pardon me, there's a missing word here, unbalanced force. So it tells us that force is equal to zero if the force is the net force is equal to zero if the object is at rest, and the force is greater than zero if the object stays in motion. And what will happen if they encountered an unbalanced force along the way? All right, what will happen is it will change. All right, it will change the status of the object. Right. Next one. The second is the second law of motion, or the law of acceleration. It states that the force is equal mass times acceleration. So what does it tells us? It tells us that that the force is somehow directly proportional to mass and acceleration. All right. So the greater the force, all right. So the greater the force is needed to move the object with greater mass, and less massive object will move. All right, will move or will accelerate greatly. All right, if you apply greater force on them. All right. So basically, the equation for this looks like this. Right? The net force is equal to mass times acceleration. And finally, we have the third law of motion, which is the law of interaction. It states that for every action, there is an equal and opposite reaction. So, the negative net force is equal to the positive direction of the net force. So, meaning to say, it tells us that if you apply force on a positive side, there is always a force on the going to the negative side. All right, so they are acting in an opposite direction. So with that, all right, that ends up our discussion with the Newton's law of motion, and I hope you did learn something from this video. All right, so give it a thumbs up if you value this video, if you did learn something from it, and comment. All right, you write down your comments in the comment section below. All right, if you have something to ask, and if you have doubts in some things that you have encountered here on this video, and if you want to be notified for future videos like this, all right, just hit the subscribe button and the notification bell. All right, so with that, okay, that ends up our discussion right here. So let's see each other next time. So peace out, everyone.